Welcome to Cosmos Day. Today we'll be continuing with electric charges and fields. Today we'll try to learn about electric fields. Electric fields. For example, let's take a charge in which it will produce electric field surrounding it. To understand the electric field, let's take a charge here. It will produce its effect around it in all direction. So at any point, its effect will be seen. In order to see this effect, which we call electric field, we are going to bring a test charge. Let's say this is a test charge, unique positive test charge, one coulomb. If I bring it near here, you'll see the effect at this point by this charge. If I increase the distance, the effect will be smaller. I keep on increasing the test charge distance, the effect will be seen very less. So it is due to the force given by this to this test charge. From Coulomb's law, we know that the force varies inversely with the distance. So as I decrease the distance here, the force increases, whereas as I keep increasing the distance, the force we see is less. So electric field is nothing but the force given by this charge to the test charge, unique positive test charge, at any point. This force is called as electric field. From the example, we have seen that if there is a charge here, and a test charge Q naught is placed at any point r distance from the charge, a force will be acting on this, then that force will give us the electric field at this point in the surrounding space of this charge. So I can define my electric field as the ratio of the force acting on Q naught due to Q to the test charge, that is a unit positive test charge. So it is defined as the ratio of the force acting on the unit positive test charge due to the charge at any point per unit test charge. Mathematically, it is given by electric field is going to be equal to force per unit charge. Its SI unit is Newton Coulomb inverse. Now, let's try to learn electric field at any point due to a point charge. Consider a point charge Q. You take any point P, r distance from the charge. You want to find the electric field at this point. So let's try to bring the test charge Q naught here. Then we can find our electric field using Coulomb's law and the electric field formula, which is given by F divided by test charge or Q naught. To begin with, consider a point charge Q. Let P be any point r distance from the charge. Then the force between the two charges, Q and Q naught, according to Coulomb's law, will be given by the force between Q and Q naught is given by F is going to be equal to 1 by 4 pi epsilon naught Q naught divided by r squared. Now, therefore, the electric field at P due to the point charge Q is given by E is going to be F by Q naught. E equals, when I put the value of F in here, 1 by 4 pi epsilon naught Q naught by r squared Q naught. Q naught is in the denominator, so it will be in the denominator. I cancel this, I get E equals 1 by 4 pi epsilon naught Q by r squared. So this will give us the magnitude of the electric field in vector form. Electric field is going to be equal to 1 by 4 pi epsilon naught Q by r squared. The direction of electric field always goes along the direction of r, so it's going to be r vector. So this is in the vector form and this is in the magnitude form. So from this formula, from the electric field formula, we find that the electric field value does not depend on our test charge. It depends only on the charge taken and the distance of the point from the charge Q naught. So electric field depends only on the charge taken and the distance of the point taken. So it does not depend on the test charge at all. Using the electric field due to a point charge, apply the formula to find the answer of these two questions, where the clues and the values are given here. Now, let's try to learn electric field lines. Electric field lines. Before we learn our field lines, let's try to know something about charge again. Charge. So, charge can exist as Charge can exist as monopole as well as dipole. Monopole means it can exist singly as positive charge and it can exist singly as negative charge. Dipole means it can exist as a combination of both positive and negatively charged. One side is positive, one side is negative. In this conductor, then it is a dipole. So charges can exist as monopole, that is singly positive or singly negative. Dipole means both positive and negative exist together. In our electric field, the direction of electric field in positive charge will be directed outward, whereas in our negative, it's going to be directed inward. The direction of electric field in positive charge is going to be directed outward, whereas the direction of electric field in a negative charge is going to be directed inward. We are going to use this concept in electric field lines. To know the electric field lines, let's take this charge, an example of this charge. We know that electric fields are coming out from this charge in all the direction in the space around this charge. Now, in order to represent that the electric fields are coming out, we're going to draw lines that will represent our electric field in the space around this charge. Electric field lines are oxymoron, I would say. Now we know that electric fields are coming out here, but we cannot see it, even though it is present. So electric field lines that are coming out from this charge are real and they are present, but we cannot see it. So in order to study the fields coming out from this charge, we draw imaginary lines coming out from this charge, and these lines are called as electric field lines. For example, let's take this. Let's say these are the electric field lines coming out from the charge, and these lines represents the electric field lines. In reality, we cannot see it, but I can draw the lines like this, straight or curve, to show that electric field lines are present. So these imaginary lines, which may be curved or straight, are called as our electric field lines, which is used to represent the electric field around the charge. So if I take a positive charge here, I can draw my imaginary lines to represent my electric field lines, which are straight in all directions. This line represents my electric field lines in a positive charge, and as we have discussed earlier, for a positive charge, the electric field is always directed outward. So these lines, which I draw it imaginarily, these lines that represent the electric field around a charge is called as electric field lines. Similarly, I can take a negative charge here. I can draw straight lines around the negative charge, and I know that the electric field in negative charge is directed inward. So this line represents my electric field lines for a negative charge. Now in both positive and negative monopole charges, the field lines are straight. In positive charge, they are going to be directed outward, whereas in negative charge, they are going to be directed inward. Similarly, I can draw field lines between a positive and a negative charge. I know that my direction for the electric field for positive charge will be directed outward, whereas for the negative charge is inwards, is directed inward. So, as I said, these lines represent my electric field lines between a positive and a negative charge. It may be straight or it may be curved. For a positive and negative charge, the field lines are always directed from positive to negative. The field lines are always directed from positive to negative. Similarly, I can draw field lines between two similar charges. There will be repulsion and the field lines will divert from one another. So these are the field lines between two positive and negative charges. Sorry, these are the field lines for a positive and a positive charges. Now you can draw a field lines for a negative and negative charges. The field lines will be same, but the direction will be directed inward. So these are the field lines for different charges. So how can I define an electric field lines? Electric field lines are real and they are present, but we cannot see them with our naked eye. But we draw it as a straight line or a curved line in order to study it in a detailed way. So this line which we draw to study it, these are imaginary lines. So electric field lines are imaginary lines which may be straight or curved, drawn around a charge to represent the electric field around it. So that is going to be our definition here. So electric field lines can be defined as it is defined as the imaginary lines straight or curve drawn around a charge to represent electric field around it. So this is how we are going to define electric field. Now we will try to discuss some properties of electric field lines. So we have learned that electric field lines which are drawn around a charge are imaginary lines which may be straight or curved. So it is one property. So they are imaginary lines straight or curved around a charge. Point number two, the field lines for a positive charge is going to be straight, which are always going to be, we can draw this infinitely, so which are always going to be infinite and are always directed outward. Two, for a positive charge, field lines are infinite straight line directed outward. Similarly, for the negative charge, the field lines are going to be straight and infinite, but it is going to be directed inward. For a negative charge, field lines are infinite straight line directed inward. For two opposite charges, positive and negative, the field lines may be straight or curved, but it is always directed from positive to negative. For opposite charges, field lines may be straight or curved, directed from positive to negative. Point number five, when I draw the field lines around all these charges, I find no two field lines that are intersecting one another, that means crossing one another. That means no two field lines can intersect one another. We'll come to this point later on, but we'll complete the properties of electric field first. Point number six, I take any point on the curved line of an electric field line. I want to find the direction of electric field. At this point, I draw a tangent from this point. This tangent direction will always give me the direction of electric field. So the tangent at any point on the electric field lines gives the direction of an electric field at that point. So on a curved line, at any point, I'll have only one tangent drawn to it. So at any point on an electric field lines, we will have only one direction of electric field. At any point on the electric field lines, there is only one direction of electric field. We'll continue with the properties of electric fields for the conductors, but for now, as I said, we'll come back to point number 5. No two field lines can intersect one another. So this will be explained by the 7th point here. I'll give it in the note. Imagine a field line which is going like this, and another field lines which are intersecting one another here. Now, at this intersecting point, I can draw two tangents with respect to one field lines and the other. Let's say one tangent field lines is here. So this will tell me the direction of electric field here. From the same point, I can draw another tangent here, which gives me the electric field direction. So if two lines are intersecting one another at a single point, I'm getting two direction of electric field, which is against our point number 7. So due to this reason, there will be no intersection of field lines, which means no two field lines can intersect one another. So we can say that no two field lines can intersect one another. It is because at the point of intersection, at the point of intersection, there can be two possible tangents that shows two direction of electric field at a point. And we know that it is not possible. So which is not possible? Now, let's try to discuss electric field lines in a conductor. Consider a conductor where one side is positively charged and the other side is negatively charged. Outside the conductor, the electric field lines will start from positive end and ends at negative end. It will be directed from positive to negative as discussed above. Now, that becomes our first property of electric field lines in a conductor. So, first point, in a conductor, the field lines are curved and are directed from positive to negative. We find that it starts from positive and ends at negative. So it has two ends. That means it does not form a closed loop like this or any shape where there is no ends. So these are closed loop, whereas we find that it starts from here positive and ends at negative. So electric field lines in a conductor never forms, or in general, electric field lines never forms closed loop. Electric field lines does not form closed loop. Now, for the third point, we find that inside inside the conductor there is no electric field lines. Why? It is because there are equal number of positive and negative charges that cancel out one another. So literally, there is no electric field inside the conductor. That means the electric field inside the conductor is zero. That is why no field lines goes inside the conductor. So point number 3, no electric field lines are present inside the conductor. To explain this, it is because there is no net charge inside the conductor, which shows that there is no electric field inside the conductor. In our today's class, to discuss the last topic, which is relation between electric field lines and field strength. First, let's try to know what is field strength. Field strength means how strong The electric field is at a point or a given area. For example, let's take a charge here, a positive charge. Field lines are coming out from the charge. Let's say I take the same area here and here. I find that only 3 field lines are passing through this, whereas 7 field lines are passing through this area here. In this region, the field lines are placed far apart from one another, whereas in this area, the field lines are closely packed, which means placed very near to one another. So, the relation between our electric field lines and field strength tells me that whenever the field lines are closely packed, my electric field strength is going to be greater, that means very strong, whereas my electric field strength in this region are going to be weaker because the electric field lines are placed far apart from one another. So, the closer the electric field lines are, the stronger is the field strength, whereas the farther the field lines are placed, the weaker the field strength is going to be. So that is the relation between electric field lines and field strength. So from here I can find that the closer we go towards the charge, our field strength will be stronger where the field lines are closely packed or closer to one another. So I can write here the closer the field lines are, the stronger the field strength is. So as we approach closer to the charge, the field lines are closely packed with strong field strength, whereas as we go further from the charge, the field lines are loosely packed, that is, further away from one another. Hence, the field strength are weaker as we go further from the charge. So this is all about the relation between electric field lines and field strength.